So first section we're going to take a look at is 1.1. This is on what we call functions and graphs. We'll talk a little bit about the graphing calculator. We're not going to get into it a lot, but I'm going to show you one thing on it, which is pretty important for all year, which is how to zoom in and out. That's important because sometimes you graph something and it's off the screen. You have to know how to find where it is. Right? And zooming will help you do that. All right, so first thing the book looks at is different types of numbers. I'm not going to write down a definition for every single one of these. I'll just quickly go through some of the types. Counting numbers are in the middle because they're the simplest, and then we build out from that. So we start with counting numbers. Anybody tell me what's the first number you would start with when you count? 1. So counting numbers don't include 0, and when you count, you go 1, 2, 3, 4. You don't count fractions or decimals. Okay, so counting numbers are basically numbers from 1 going up, no fractions, no decimals. The problem with just counting numbers is when you get into arithmetic, there are certain types of problems you wouldn't be able to do with just counting numbers. Addition would be okay. If you take a counting number and you do addition with another counting number, you'll be okay. The problem would come with subtraction. Somebody give me a counting number.
23.
23. Well, if I do 23, which is a counting number, minus 23, which is a counting number, I'm subtracting two counting numbers. But the answer is not a counting number. There's a name for that. I'll tell you what that is in a minute. When you subtract two counting numbers, it is possible you don't get a counting number. So what are we going to do? Well, we're going to have to invent something that would represent the answer to that number, and that's where whole numbers come in. The only difference between whole numbers and counting numbers, whole numbers include 0. That's the difference. But we could still run into a problem. Addition would be okay, because if you take any whole number you want, add another whole number, you will get a whole number as the answer. So addition would be fine. But subtraction, let's take a whole number, like 3, and let's subtract another whole number, like 4. So the problem with whole numbers is you can get an answer that's not a whole number when you do subtraction. We don't want that. We want to be able to get an answer. Maybe in first grade, or if I wrote that problem down, they'd put a question mark saying you can't take away more than you have. But we know we can expand the types of numbers we work with to put that symbol in front of them. And that symbol means having even less than 0. So we start to get into negatives. And that's what integers are. Integers include all numbers that are not fractions or decimals, positive and negative. And 0. 0 is neither positive or negative, but it includes 0 as well. Think about addition. If you picked any integer you wanted and added it to any other integer, would you always get an integer for the answer? Then what that means is integers are closed under the addition sign. Meaning if you add two integers, you'll always get an integer. That's called closed. How about subtraction? If you subtract two integers, will you always get an integer? Yeah, that'd be fine. Multiplying. If you multiply an integer times an integer, do you get an integer? Yeah, that's fine. How about division? If you divide an integer by an integer, will you always get an integer? So now we have a problem. That means integers are not closed under the division operation. You can get something that's not an integer. That's bad. So now we need to figure out, okay, what are we going to do? That's where we expand it to rationals. So now, a rational number is basically a fraction. Specifically a fraction where the bottom is not 0. You can never have 0 in the bottom. And you have a number that's an integer in the top. So an example, 3 divided by 4. That's an impossible problem if you don't have rational numbers. Because if you asked me to take like 3 objects and divide them equally between 4 people, I can't do that. I can't give you these, I can't have 4 people in front of me and give each person an object. I can't divide 3 by 3. But what I can do is if you allow me to take an object and break it into pieces, I can break this into 4 equal pieces and divide it, out to whatever I had to do, right? So I can divide things into fractions or pieces of a number. And that's where rational numbers come in. I'd say for most everyday kind of purposes, rational numbers are about as complex as you would need. Think about like if you get gas. A lot of times it's a dollar amount, but then there's a fraction. Some people do it exactly like $23, but if you just fill it, it's probably going to come out to like $40.52. That 52 is a fraction. When you're cooking, you might need something between 2 cups and 3 cups of flour. You might need 2 1/3, right? It's a fraction. When we start to get beyond rational numbers, now we're getting into numbers that aren't used in everyday life as much by just like regular people that use basic math, right? Irrational numbers are starting to get a little more complicated. So rational numbers can be written as a fraction. So irrational numbers, what do you think? They cannot. They cannot be written as a fraction. Can anybody think of a number that is irrational? Yeah?
It's the most basic rational number, pi.
So pi, that would be an irrational number. How about,
Square root of 2.
Yep, square root of 2. Basically, the square root of any number that's not a perfect square. Square root of 2, square root of 3, square root of 5, things like that. Now, you might think like, well, can you actually prove that square root of 2 can never be written as a fraction? You can. You can prove that it can't be done now and it will never be able to be done a million years from now. It is absolutely impossible to write square root of 2 as a fraction. It can never be. Again, what's the use for square root of 2? A decimal that goes on forever? Well, in most, like let's just take the square root of 2. You get that decimal. Well, if you were machining something or you were building something and you had to use the square root of 2 for some reason, you're going to round this off at some point. You're not going to use this entire number. I mean, that'd just be way too much precision. If you were machining something, you can't machine something that precise. I mean, maybe you can go to the 10,000s, 100,000s. Can you machine something to like a millionth, 10 million? I don't know, maybe. But you're not going to be going that many decimals out. So what's the practical use for that? Well, now, we're getting out of practical uses and more theoretical, higher level type of math stuff. Right? So square roots, pi, and together, if you take all the numbers you can write as fractions and all the numbers that you can't, that's called the real number set. And just to explain how this works, everything that's a counting number is a whole number. But everything that's a whole number is not automatically a counting number. And if it's confusing, think of it as places. A small place to a bigger place. Think of this as like Boston, Massachusetts, New England, United States, and Earth. So think of it that way. If you're in Boston, does that mean you're in Massachusetts? Yeah. But if you're in Massachusetts, you're not automatically in Boston. It doesn't work the other way. And if you're in Boston, then yes, you are on Earth. Okay. So it works. That's how it works. Any questions on those number systems? Yeah.
What about like isn't that like an I symbol?
So that gets into complex and imaginary numbers, which we're not going to talk about yet, but yep, we will. Yes, we will touch on those. So some of these have names. Well, some of them have abbreviations. So when we talk about the set of integers, a lot of times we use that symbol that looks like a Z. It's got an extra line. When we talk about rational numbers, we can use the letter Q with that line. And the set of real numbers, capital R, again, with that like extra line. Those are the only number sets I know of that have abbreviations. And those will come up here and there. What do you think it would mean if I did something like this? If I wrote that down, what do you think I'm referring to?
A positive rational number?
A positive rational number. Yeah. So you can have positive rationals, negative rationals, things like that. Any questions on any of those symbols?
Do you know where the letters came from?
I don't. I can just guess. I mean, R for reals, and Q. My best guess for that is quotient. When you divide two numbers, you get a quotient. The Z, I'm not sure. I read something once, something about what they call integers in German. Begins with a Z, but I could be wrong. That could be fake. What I read. But yeah, I don't know why the Z is there. It's a good question. So in math, we have four basic, what we call binary operations. A binary operation is an operation that takes two numbers to make it work. You can't add one number. You can add two numbers together, but if you want to add numbers together, you need at least two of them. Same thing with subtraction, multiplication, and division. Can anybody think of an operation that doesn't need two numbers? You could just plug in a single number and do this to it. Yeah?
Square root.
Yeah, you could do square root. That's not a binary operation. It just takes one number. Yep. But these all take two. So we're going to look at some special properties. One of them I already kind of hinted at to you, the idea of something being closed, or closure. And in these properties, I'm going to use the letters A, B, and C to represent real numbers. So this is looking at all properties with addition, I believe, just addition properties. And the idea that if you take a real number and you add another real number and the answer is a real number, that's called closure. Okay? It means that whatever types of numbers you started with, the answer is also the same type of number. And it always works with addition. We saw problems with subtraction. Right? So if I asked you, are whole numbers closed under the subtraction operation? The answer would be no. Because you can do a whole number minus a whole number and get something that's not a whole number. To be closed, you start with a type of number, you do an operation, and you end up with the same type of number. Any question on that idea? So addition is closed under the real number system. That's what you could say. Commutative. Can somebody explain to me what that would mean for addition? It's commutative. Yeah, Ronald?
Is the commutative one where you can swap around the numbers and it'll be the same?
Oh, I'm sorry, you go by Jasper.
Yeah.
All right. Yeah, you can swap the numbers. So like you could have 2 plus 5 equals 5 plus 2. Right? That's commutative. How about associative? Anybody remember that one?
I haven't heard these terms in so long.
Think about when you associate with somebody, or when you associate, do you do that alone or do you do it in a group? You do it in a group. So associative has to do with group. Something with grouping, yeah?
Would it be like A times B equals AB, or?
That would be the commutative property of multiplication. I'm not going to write down any of the multiplication ones. I just put a reference to them in your book.
Okay.
But all these properties that we're doing are also applicable to multiplication.
Okay. Then I.
But anybody remember what it means? So associative has a grouping symbol. So what symbol in math is a grouping symbol? Parentheses. So associative doesn't have to do with the order. It's the same order on each side. It has to do with how you group things. What do you do first? Do you want to add B plus C first? Or do you want to do A plus B first? So associative is how things are grouped. And that property applies to addition, and it also applies to multiplication. not necessarily subtraction. If you group things in a different order with subtraction, you could get different answers. Identity. The identity property is what you can do to something to get the same thing back. So what can you do with addition that doesn't change the result? Yeah, Leah? Add 0. Good. Now the identity property for multiplication would not be multiplied by 0.
Would it be by one?
Be by 1. Okay, so the identity property a little different, but it's the same idea. The inverse property is what you can do to a number to get 0. What can you always add to a number to get 0? Yeah? Yeah, it's opposite. If you take a number and add its opposite, you get 0. Okay, that's called the inverse. And distributive, that's one you use all the time, so most people remember that one. It's when you have either addition or subtraction inside parentheses, and you distribute what's on the outside to what's on the inside. Distributive is not a property that applies to multiplication, but you absolutely do not use distributive property in an example like that. No way. So you won't find a distributive property for the multiplication properties. It only applies when you have addition or subtraction inside parentheses, not this. Okay. Any questions on those properties? Okay, so we're going to cover quite a bit today, but again, I think it's all going to be stuff you've done in Algebra 1 or earlier. What does it mean to have an equation? It's when you put an equal sign between two expressions. Remember, an expression in math can be just a number. It's an example of an expression. Or it could be an algebraic expression. But if you put an equal sign between two things that are expressions, there you go. You just created an equation. And an equation is something you can solve. An expression is not something you can solve. I couldn't say, here, 5x, solve it. 5x, what? 5x equals 10? What is it? What do you want? Those are all examples of equations. What's going on with this one? Yeah?
Well, it's incorrect.
Yeah, this is a contradiction. That's the kind. It's an equation, but it's a contradiction. So it's not right. How about this one? There's a name for that one too. Yeah.
Is it expanded? Well, it's not simplified.
Well, you're right. It's not simplified. If you simplified it, it would say 7 equals 7, which is definitely an equation. And does anybody know what kind of equation that is? Begins with an I. Yep.
Identity.
Very good. That's an identity. An identity is an equation. That is always true.
Oh, we just went over that.
And this, well, is it true or is it false? Well, the answer is it depends. What are you going to fill in for x? That's a conditional equation. It could be true under the right condition, in this case, letting x equal 6. But they're all equations. So we looked at some properties involving expressions, like taking a plus b, making it b plus a. Now we're going to look at some properties involving equations. Let's start with this one. A equals A. Something is always equal to itself. Does anybody remember what property that is? So not an identity. It's a little different. Identity is when you do an operation like plus 0 and you get itself back. Yeah? Reflexive. Yes. So that's called the reflexive property. It basically says, where do you see something like that? A lot of times when you do a proof, and you have like a triangle, something like this.
Are we going to be doing more two-column proofs this year?
No.
Okay.
Unless you want, we could.
No.
But alright.
So you might have two triangles like that, and you would say that that side is congruent to itself because it's used in both triangles, right? So that's reflex. How about this one? If A equals B, then B equals A. Yeah?
Symmetric.
That's symmetric. Symmetric just means like if you end up with an answer 2 equals x, you could rewrite it as x equals 2. You are allowed to switch what's on each side of the equal sign. That's not commutative. We're switching what's on each side. We're not switching two things within the same side. Difference. And how about this one? If A equals B, and we know B equals C, then we know A equals C.
Oh, shoot.
Yep, that's a transitive. And transitive can have, this is a simple transitive, it's just a chain of really 3 things. You could have a chain of 10 things. But the point is, that's transitive. Okay.
Sorry.
Question?
You get my paper.
So what I want to do here is I'm going to give you, bless you, I'm going to give you a step, and I want you to tell me the name of the step. So let's say I did this. We're trying to prove that what's on the left and what's on the right are the same thing. So this would be the first step. What would be the name? I would give you that. Now you tell me the name of what I just did. Toronto? That's a distributive property, yep. And I'm really breaking this down. So now, what if I did this? And it's not really a great word for what I just did on the left-hand side, but what did I basically do to the left-hand side? I just, what? Yeah, I just simplified it. And now, I'm going to say 6 plus 2x equals 6 plus 2x. What property did I just use on the left-hand side that time? The commutative. Yep. So this kind of problem I could do 2 different ways. We could do it the way we just did it. You tell me the steps. Or I could tell you the names, and you show me what to do at each step. Any questions on that? So that's basically, that is a proof. I mean, it's not like a geometry proof, that's an algebra proof. You proved that the left-hand side equals the right-hand side. Here's all your, names of your properties, and now you just showed me the property. That is basically a proof. All right, coordinate system. We'll do 1D first, and we'll get into 2D. So, coordinate system, if you have just a number line, 0 in the middle, positive numbers to the right, negative numbers to the left. When you create a number line, essentially what you're doing is you're giving order to things. You're creating like a hierarchy of numbers, where some are bigger than others. Bigger numbers are always to the right, smaller to the left. Once we start saying things are greater than or less than, we need symbols for those names so we don't have to write it out every time. So let's just make sure we remember the names of those 4 symbols. What's the top one? Sam. Next one? So you put the line under it, means equal to. This one? And the last one? Good. And together, those 4 symbols are called what? Yep. Inequality symbols. Yeah. So these are your 4 inequality symbols. They don't mean equality. That's an equal sign. They mean inequality. They are not the same. Except in the case where it could be equal to as well. Less than and greater than strictly means something is smaller or bigger. It's not equal to. Questions on this? So, graphing on a number line. There's two ways to do it. I'm going to show you this way first, which is probably what you're used to doing, and I'm going to show you how our book does it. It's just slightly different, but it's pretty similar. If you want to graph something like x is greater than or equal to 2, there's really two steps. First, you have to put a circle on the number 2. You have to decide if it should be an open or a closed circle. By open, I mean not filled in. You use an open circle if you see either one of those symbols in the problem, less than or greater than. You use a closed circle if it has the equal to. The way I remember it, if the symbol has an extra line under it, then you have to take the extra step and fill in the symbol. So let's try an example of graphing x is greater than or equal to 2. So first thing, we decide what kind of circle we're going to use. Then we decide what number we're going to put it on. And then we have to shade in the correct direction. All right, so if we had a number line, let's just go 0, 1, 2, 3. That's enough. First of all, what kind of circle would this problem use? Open or closed? Closed. On what number?
2.
2. And you want to shade all numbers that are greater than or equal to 2. So which way are the numbers greater than 2?
Right.
To the right. So we could shade that way. Now, some people say, well, yeah, you can just go by the way this inequality points. And you can, as long as what? Jackson?
As long as the variable is on the left.
If the variable is on the left. That means exactly the same thing. And if you look at that and you say, oh, it's pointing to the left, I should just shade to the left. You can't go by that because the variable is not in the proper spot. If the variable is on the left and the number is on the right, then yes, you can go by the way it points. Questions on it? Okay, let's try this one. But let's fix it first so that it's, I call it like the standard way you would write it with the variable on the left. How would you fix this so the variable's on the left? Yeah, Angela?
You flip like the direction of the sign.
Whoops.
Yeah, the other way. And then now you can put the variable on the left and then the number on the right.
Right. So when we do that, it was pointing at the y when we started. It's still pointing at the y, so it means the same thing. And I had it over there too. So y is less than 3. So on our number line, let's just go 0, 3, negative 3. You'll have questions like this on Edge Elastic. It's pretty simple though to do inequalities. I'll show you how to do it. What kind of circle do we need? Open. Where do we put it? 3. And which way do we shade? To the left. Okay, so I'm guessing most of you have done graphing like that. Open circle, closed circle. Well, there is another way to do it, and this is the way our book shows it. It uses brackets and parentheses. Bracket takes the place of a closed circle. Parenthesis takes the place of the open circle. So if you wanted to do the same problem that we just did, and you wanted to graph greater than or equal to 2, the only thing you have to think about ahead of time is the bracket should face the way you're going to shade. So with the circle, you don't really have to think about that part. But with the bracket, it should open the way you're going to shade. So I'm going to shade to the right. So my bracket should look like that. And we shade. If a problem asks you to graph something, I don't care which way you do it. The point of this is, if you see this on a test and I say, write an inequality, and I give you this picture, you would have to know that this means that. One thing you don't want to do is mix them. I would say just stick with, one or the other if you're going to do graphing.
So parentheses, the open circle you said.
Yep. So if we were going to do this one, because it's a parenthesis, or I'm sorry, because it's a less than, you're going to use a parenthesis in place of the open circle. So bracket takes the place of the closed circle, parenthesis takes the place of the open circle. Where would my parenthesis go for this one? And which way would it face? To which way?
It would face to the left.
Yeah, it's going to open to the left.
Yeah.
Yep. So just like that, and then shade this way. Okay. Any questions on that? So another type of inequality, this is a conjunction, and a conjunction has the word and. A conjunction is an inequality that you can actually shorten instead of writing that. What's in that black box is exactly the same as what's in that red box. And if you're wondering where does that come from, if you break the box up and look at that part, x is greater than or equal to 2. That's that part. And then if you look at x is less than or equal to 9, that's that part. So it's like the middle is used twice. It's used with the part on the left and the part on the right. So you should be comfortable with either taking something that's written as the word and combining it into a single conjunction with two inequalities, or taking something that's written without the word and writing it with the word and. Any question on how to go between these two? All right, let's graph now. Now, this is especially the kind of problem you want to stick with either the circles or the brackets and parentheses. Pick one or the other. Don't use both. Right, so let's go 2, 6, 8, 10. All right, so let's start with the part on the left. X is greater than or equal to 2. What kind of symbol should I put on the 2? Yeah, Jackson?
Either closed dot or bracket.
Okay, let's do the closed dot. And which way are we going to shade?
To the right.
Okay, I'm just going to put an arrow telling me I'm going to shade to the right because I have more of this picture to think about. And that's going to control, like I just don't want to keep shading forever because you're going to see what happens. What kind of circle would I put on x is less than or equal to 9? Yeah, Jameson?
Closed.
Closed on 9 and shade which way?
To the left.
To the left. So essentially, where am I shading? In the middle. This is a between. And that's how most conjunctions turn out. You end up shading between. Any questions on it? Sometimes it could be two open circles. Could be an open and a closed circle, or two closed circles. Depends on what these two inequality symbols are. Okay, absolute value. It's pretty simple. If you had to define absolute value, how would you define it? Yeah.
How far away the number is from 0?
Yeah, that's a very visual way of thinking about it. It's the distance from 0 on a number line. If we wanted to think about it a little bit more formally, like if we wanted to program a computer to be able to do it, you'd have to be able to give the computer a very specific direction on how to find absolute value. The calculator can't just the computer can't just measure distance. It doesn't know how to do that. So there's really two cases for absolute value. Sometimes you have to do something to the number, sometimes you don't. What kind of number could I give you that you really don't have to do anything to it when you take the absolute value? If it's what kind of number? Yeah.
Positive.
It's already positive, or even 0, which isn't positive. But 0 and up, you don't have to do anything to the number. If you get a number that's greater than or equal to 0, put the same number down again, and that's the absolute value. But what about if you were less than 0? What would you have to do to the number? Yeah?
Multiply by something.
By what?
By -1.
By -1. Yep. You have to multiply it by -1. That's a very concrete way to describe absolute value, something that a computer would understand how to do. Either give you back the same number you started with, or give you back the opposite of the number you started with by multiplying by -1. Any questions on that? Of course, we don't really have to think of it this way when we do it in our head. It's just, we just can do it just because we have practice doing it. That would be a way you could program to do it. So, absolute value of 6. 6. Absolute value of -3? 3. Easy enough. Questions on that? Distance. So this kind of ties in with what we just talked about. When you think of a distance, what kind of number does distance always have to be?
Positive.
Always has to be positive. An absolute value will guarantee you never get a negative number. So if you had 2 points on a number line, A and B, how would you find the distance between A and B? Yeah?
You subtract like one from the other.
Yep.
B minus A, right?
Sure. Or A minus B. Really could do it in either order.
The absolute value of that.
As long as you take the absolute value. Because people say, well, if you do subtraction, the order matters. It does, but if you take the absolute value, it doesn't. So you can subtract A minus B or B minus A. If you take the absolute value between the two, you'll get the distance. So if I wanted to write down how to find the distance between -2 and -9, what would I write down for a calculation? Yep.
It would be like the line, and then it would be -9 or -2, and then
Yeah, it doesn't really matter. We can do -2 if you want to do it that way.
okay, and then minus -9, and then the other line.
That would be the calculation that you would do. And Ben, if I do -2 minus -9, what do I get?
It's just adding 5 and 9, so you would get 7.
You get 7. This is really -2 plus 9, which is 7. And you know the absolute value of 7 is 7, which means those two numbers are 7 units apart. Yes?
If absolute value is like part of an equation, would that treat the numbers inside of it like their parentheses? So like, would you do everything inside of the lines before you make them positive or anything like that?
Like using time density.
That's usually the kind of equation you're going to see that would have absolute value in it. So there's really nothing to do inside here because you have a variable and a number.
Okay.
What's going to end up happening, we'll talk about this probably next week, is you have to split it into two
Positive,
equations.
a positive and a -1, right?
An x minus 3 equals 4, and x minus 3 equals -4. But yeah, I don't think we're going to do that today. That's generally what would happen. Hey, any questions on that? All right, so we did 1D. Let's go right into 2D coordinate system. Quick review of that. Somebody tell me some important things about a two-dimensional coordinate system. Tell me anything you know about it. Yeah?
0, 0 is the origin.
Yes, the coordinate 0, 0 is called the origin. What else?
The coordinate has 2 numbers.
Yep, to specify a location on this system, you need 2 numbers. Something, something. All right, what else? Jackson?
It runs on the x and y axes, with the first number being on the x-axis and the second number being the y.
Yep, so we have an x and we have a y-axis. And what do the x and y-axis separate the coordinate plane into?
Oh, quadrants.
Quadrants. I think that's a big. So we have x-axis is horizontal, y-axis is vertical. Where they cross is the origin. Coordinate, the quadrants are numbered 1 through 4, starting with 1 in the upper right and going counterclockwise. 2, 3, 4. The parentheses next to each quadrant number is the type of coordinate you would see in that location. In quadrant 1, all coordinates are a positive, comma, positive. Okay, quadrant 2, negative, comma, positive. What else? Just like a number line, positive numbers go to the right, negative numbers go to the left. For the y-axis, it's a little different because we didn't do a vertical number line. Positive is up, negative is down. And what do you call this thing? That thing I just circled?
Coordinate pair.
Coordinate? Can you be more specific than a coordinate? An ordered pair, yes. So an ordered pair is a specific type of coordinate. This is also a coordinate. It's not an ordered pair, it's an ordered triple. Ordered pair is a two-dimensional coordinate. Questions on that? A lot of stuff today, but I hope it's mostly review. Okay, not review. Zooming on a graphing calculator. So sometimes we might have something that we can't see because it's off the screen. So what I'm going to do is I'm going to show you how you can change the window on the calculator to see something that might be off the screen. So first thing you want to do is turn it on. And you should be at this screen. And the next thing is I already have stuff in my graph. I want to get rid of that. So when you're at the screen, if you press y equals, I don't want to have anything written there. So everyone should see this y1 through y9. Anyone that doesn't see that?
What did you press?
Y equals. Yep. So what I want to do is I want to clear that. So the clear button is all the way on the right-hand side, just below the four-way directional pad thing. Just hit clear. If you have anything, hit clear. And hopefully you have a screen that looks like that. Everybody have that? Okay. So this part, I just want you to watch me because I'm going to do something. Actually, no, you can do this part too. So what we're going to do is we're going to set a standard window. Okay, the standard window on a graphing calculator is -10 to 10 on the x-axis, -10 to 10 on the y-axis. I know it says -20 to 20. I'm not doing that yet. So I want to press zoom. And the standard window is 6. It says standard zoom, or zoom standard. So when you go to zoom, I want you to press 6. And if you look, you should see 10 tick marks going left, 10 right, 10 up, 10 down. Any question on how to get to that? What I want to do now, this part you can just watch. You don't have to type this in. I'm going to type in x squared plus 10. And I'm going to hit graph. And I just want you to watch what happens on my calculator. When you see a little circle in the upper right spinning yellow, that means it's thinking. When the circle stops, it's done. So my calculator is done. Where's my graph? It's off the screen. We're going to learn that's a vertical shift 10 units up. So this is a parabola that normally would have been at the origin for its vertex. It's been moved 10 units up, which is out of the standard window. So let's fix that by setting this. You're being given 4 values. If you go to window, the 4 values that you have here, -20, 20, -20, and 20, are these 2 numbers and those 2 numbers. This is the lowest the x-axis will go. This is the highest the x-axis will go. When you're given a window, you're always given the x values for your window first and the y values second. Another thing that's important is the max has to be bigger than the min. It wouldn't make sense otherwise. That'd be like me saying to you, pick a number greater than 10 and smaller than 5. Goodbye. So, the min has to be smaller than the max. You try typing it in the wrong way. you'll get an error on the calculator. This is the y minimum. So it's the lowest the y's will go. That's the y maximum. So we're going to type those 4 numbers in these 4 spots. So for x min, you just put in -20. It is important you use the negative symbol at the bottom. The negative symbol on the right-hand side is not a negative symbol. That's a subtraction sign.
Okay, I just plugged it in on top of it instead.
Yeah, so this symbol will not work. Okay, that's subtraction. That's a negative. Big difference. X max, we want 20. Just keep pressing the down arrow. Y min, we want -20. Y max, we want +20. The other thing, that the X scale and the Y scale, not really important. That's just how many tick marks are going to be on the screen. We're never really going to be counting tick marks for anything. So I don't really care if you put a tick mark every 1 unit, or if you didn't want to see as many, I guess you could put one every 5 units. Not important. Okay, so don't worry about that. And then just hit graph. Now you might not see anything other than more tick marks squeezed together. But me, I had something that I couldn't see before because my standard window was basically right there. I didn't have to zoom out in every direction to see it. The only number that I actually had to change to see my graph was that one. If I had just changed the Y max to be higher, I would have seen this problem. I didn't have to go down here, or over there, really. I did, but I didn't have to. So any questions on that? Setting your X mins and maxes to zoom out. So you'll have some problems in the homework where you just have to practice zooming, and that's it.
What's it behind the box?
I just said set your rectangle to a zooming, or set it to a viewing window of that. You might see the textbook call a graphic calculator a grapher.
Grapher?
It calls it a grapher. So if you see something that says use your grapher, it just means graphic calculator. Again, you don't have to do this, but if you change the scale, like if you change it to a 5, I think you'll be able to tell. You just see tick marks less often. So now they're putting a tick mark every 5 units instead of every 1 unit. Again, you never sit there and count tick marks on the screen, so that's not really important.
Can you also make it a fraction to make it more?
Yeah, you could do like, if you put a tick mark every 0.5 units, now you're going to see so many of them, it's probably just going to look like a mess.
It's going to look like a solid line.
There's just too many of them for it to display correctly, and there's not enough pixel resolution on the screen to really show it. Yep. So that's what the scale does. Are these the last 2 things? Yep. Good. Okay, so last 2 things. So distance formula and midpoint formula. We looked at how to find the distance between 2 points on a straight line. Well, in 2D, they might not be in a straight line. Might be like that. So, if you think about it, let me pull up a background. Let's do this one. I think this one will be okay. Yeah, maybe you can see that. Let's see if I make the squares a little bigger. Yeah, that's good. All right, so let's say we had a point here, and then we had another point over here. And I want to find the distance between those 2 points. Well, I can't just count. If they were perfectly horizontal, that's easy. I could just count. 1, 2, 3. Right? That's the distance between them. This is going at an angle. So anyone have an idea of something that I could count or maybe a shape I could make out of this and then count that would make it easier to work with. Because this distance is really hard to find directly, but I'm going to be able to find it indirectly. Yeah. Yes? Yeah, we're going to make a triangle out of it. So the way we're going to make a triangle, we're just going to take a horizontal and a vertical, and we're going to put them in. I don't need that many. We're just going to put them in, like right here. It's longer than I need, but that's okay. Point is, I just made a triangle. Now, what distance can I easily find in that triangle? Yeah? I can easily find the height, 2. I can find the base, 1, 2, 3, 4, 5. And how could I use those 2 numbers to find the real thing that I want to know? Yeah?
Pythagorean theorem.
Yeah, Pythagorean theorem. So really, we're just going to do the Pythagorean theorem. That's the distance formula. The only difference is you would have a number here, like this would be a 1. This is a 6. How do you get 5? Like if you couldn't count it, you didn't have it on paper, how do you get 5 from 1 and 6? Yeah?
You subtract.
You just subtract them. And same thing here. This is at a height of 1. This is 2. This is 3. So this is at a 1. This is at a 3. How do you figure out the height? Take the difference between 3 and 1, and you get 2. So when I put up the distance formula, it's going to look a lot like the Pythagorean theorem. You subtract 2 numbers to find the length of the base. That's what this is. You subtract the y values to find the height. And then once you know the base and you know the height, you square them, you add them up, and you take the square root. That's the Pythagorean theorem. So that's the distance formula. All right, so let's try finding the distance between those 2 points. Since this formula has kind of a lot in it, parentheses, exponents, I like to write it all out first and then fill in my values. So I usually go like this. Then I don't forget to write anything down that's part of the formula. All right, Caleb, what would go right here?
Would be 1?
Yeah, you could have done the 1 or the 5. Now that he decided the 1 is going to go there, everything else is pretty much automatic. Leo, what's going to come after it? That's going to be the 5. So there's the difference in my x's. And what about here? It's going to go there. Yep, Savannah?
6.
So we're going to have, well, let's just satisfy my OCD. Let's go in the same order.
Yeah, I did. You wanted to after the subtraction sign.
Yeah, what's the whole thing?
4 minus 6.
4 minus 6. All right, so we got 1 minus 5, 4 minus 6. Close it, and now we simplify it, and that's going to be our distance. So 1 minus 5 gives me, and then square it, 16 plus 4 minus 6 squared, 4. So that's the square root of 20. But because a perfect square divides into 20, we need to reduce that square root. I don't mean change to a decimal, just simplify. Yep.
That would be 2 square root of 5.
2 square roots of 5. Good. Any question on how to reduce a square root? That's the whole reason I did the distance formula, just to remind you how to reduce square roots.
Do you just have that one memorized at that point, or did you break it down in your head?
I don't know. How did you do it, Jorma? What did you?
Oh,
Did you actually do it out?
I kind of wrote down 20.
He broke it down. So, for me, yeah, I have that one memorized. But in general, if I didn't, like let's take 60. I don't know what that is off the top of my head. I try to think of the biggest perfect square that I can that goes into 60. So some people make a whole tree. So I do it a little differently. So if I try to find the biggest perfect square that goes into that, I think it's 4 times 15. And then I say, okay, 4 times 15, take the square root of each number. 2 square root of 15. That's how I do it. There's other ways to do it, but that's just how I do it. So find the biggest perfect square that goes into that number and whatever's left. Now, if you don't find the biggest perfect square, that's okay. You could end up doing the problem twice.
You remind me what a perfect square is?
Perfect square, a number you can take the square root of without it, and it comes out to an integer. Square root of 4, 9, 16, 25, 36, things like that.
I have to go to the bathroom. Did you want us to ask or do we just gotta go?
Just come on up so I can sign your agenda, and when I see your agenda, I'll know where you're going. So that you don't have to ask me if you don't want to. You can just show me your agenda. And then sign out here. Any other questions on simplifying a square root? An example of one, if you didn't do the biggest one, you could first. Let's say you had, let me think, 48. Some people may say, oh yeah, I can do 4, right? I can do 4 times 12, and that's okay, because you got, oh, let me sign that for you. You can take it with you or not. You don't have to. Okay, I'll just.
Yeah, right.
Yeah. Thanks.
This is the first time I've actually to do this.
That's fine. So 4 times 12 gives you 48. Take the square root of 4. 2 square root of 12. You might say, well, what's wrong with that? Well, what is wrong with that?
12 can be simplified.
Yeah, 12 can be simplified again. So now you got to do 2, and you can do square root of 4 times square root of 3. So that's 4 square roots of 3. If I had just found a bigger perfect square that went into 48 to begin with, I could have done that in one step. I could have done 16 times 3, and that would have done this whole problem in one step. It's not, you don't have to do it in one step. You do have to get to the simplest result you can in one step or 2 steps or however many you need.
Wait, wouldn't 16 times 3 be 2 steps?
Well, I mean, you could write it, so if you had the square root of 48, you write it as 16 times 3, and then you're done in one step of the square root versus having to break it up twice. But again, breaking it up twice, that might be good. If you had a really big number, maybe you want to break it up twice to make it smaller, and then it's easier to work with.
Could you explain how you got simplified the 2 times the square root of 4 times the square root?
So square root of 4 is 2, and 2 times 2 is 4.
Oh, yeah.
Yeah, I would show all that out, like algebra 1, but that's how you end up doing it.
I forgot that those 4 was
Midpoint formula. Why? Well, just because usually when you do the distance formula, you do the midpoint one with it. Just a little easier than the other one. And this involves adding 2 things together and dividing by 2, and then adding 2 things together and dividing by 2. Well, there's a name for that. If you add 2 things together and divide by 2, what does that give you? Yeah?
It's the average.
It's the average. So really what the midpoint formula is it's the average of the x's, what's in the middle, and what's the average of the y's. That's the midpoint formula. So if you think about it that way, it's a pretty intuitive formula. You're averaging, and then you're averaging again. Right. So let's find the midpoint between those 2 points. And that'll be the last thing. So, in this case, what would be x1? Angela?
3.
Okay, so we can do it that way, 3. What's going to be x2? -5. All right. How about y1? And we'll follow the same kind of pattern. That would be the 7, and y2. 2. All right. So there's your formula, and then we just simplify as much as we can. What are we going to get for the first number? Yes, -1. And the second number? You could write 4.5. You could just leave it like that if you wanted as well. Either way. All right, so a lot of different stuff. I would say most days we're going to focus a little bit more on one topic. That was like maybe 6 or 7 different topics, but a lot of review. So the homework, it's going to skip around because we did like 7 different things. So I'm going to give you like 1 or 2 of each type of thing that we did. Okay, so that's the homework for tonight. Doesn't skip around too bad, but it's a little bit. So 1 through 16, 20 to 23, 30 to 32, and 38 and 44. So we'll take a look at that tomorrow. And then tomorrow we'll do our second lesson, which will be the last one for this week.